This Quaker burial ground is dedicated to the memory of George Fox, who in 1653 wrote of the empty Derwent Valley, "The everlasting word of life was freely preached over those dark countries, and many hundreds were turned to Christ, their teacher."
I have much pleasure in declaring open the Derwent Reservoir. I am very pleased to be with you all today to see in the Derwent Reservoir the culmination of so many years of thought, planning, hard work, and brilliant engineering. Anyone who has had any hand in the construction of this great undertaking must feel justly proud. I am sure there were times in the past 6 years when the difficulties appeared almost insuperable, and no doubt there were many who felt that this part of the country was doomed forever, its natural beauty lost beneath a mass of machinery. The fact that instead something so beautiful and yet so eminently utilitarian has been produced is a lasting tribute to the skill and ingenuity which has gone into the work.
One does, of course, realize that one has been responsible for bringing about a very substantial change. I quote the very delightful residents of Millshields Mill, now under some 70 or 80 feet of water. And I had lunch there with the then owner in preliminary attempts to discuss valuations and so on. A glorious old house, beautifully furnished. And when the owner's wife said to me, "Mr. McClellan, do you realize what you're doing to us, putting this under 80 feet of water?" I said, "I do. It makes me sad, but I have a duty to do." We, as a water undertaking, were determined from the beginning to tell all the people all that we were doing. I sat in farmhouse kitchens and discussed with very worried farmers where we might possibly put the dam.
3 positions were investigated before it was decided that the site near Derwent Bridge was the most suitable position for the Derwent Reservoir.
A concrete dam at Derwent would have been quite out of the question, because in the middle of the valley, the solid rock is covered by nearly 200 feet of various clays, silts, sands, and gravels. Earth dams, on the other hand, have a broad foundation and apply a much lower intensity of loading, and they can be successfully built on a soft, compressible foundation.
The weakness in the foundation is due to a thick layer of clay which lies as much as 80 feet below the ground surface, and this clay had to be strengthened by means of sand drains before construction of the embankment could commence. This involved a total of 4,475 drains.
The sand drains consisted of 11-inch diameter holes which were drilled using a fluid of mud to support the sides of the hole from caving in. This mud was then washed out with clean water and replaced with sand.
The secret of success was speed of movement between the holes. This was done by the manufacture of long hydraulic jacks which were positioned one at each corner of the rig, and the whole contract was planned to be completed within 86 weeks. In order to form this lake in the Derwent Valley, we wished to construct an embankment consisting of earth across the valley at a point where the valley was 3,000 feet long. Now, in order to do this, it was necessary to divert the River Derwent into the hillside. So the first task on arrival for the contractor was to drive a tunnel 2,000 feet long and 17 feet in diameter through the hillside and connect this tunnel to an inlet channel and an outlet channel. This would then enable the riverbed to dry up and for work to proceed on the construction of the earth dam. Unfortunately, the ground in the tunnel consisted of a mixture of sandstone and shale and was not easy. When the miners were driving the tunnel forward, they had to take particular care to ensure that it did not fall out. This entailed erecting steel ribs, 3-foot centers throughout the tunnel.
The outlet channel, which was programmed to be completed in a year, was a difficult problem. As soon as excavation started, using drag lines, running sand and fine water-laden silt was disclosed just below the surface. The channel was to be 30 feet deep with 3-to-1 side slopes to be covered with concrete blocks, topsoil and grass. The very fine silt was on the borderline for dewatering, but after laboratory tests, it was decided to install a 2-stage system of well points at close centers using the sanding in method. 6-inch pumps assisted by separate vacuum pumps had to work day and night for 9 months and made it possible to excavate and work in dry conditions.
I probably missed some of the worst of it, which at the beginning in the outlet channel, I came at a stage where the various other deep excavations were going ahead, and although I've worked on civil engineering and building for many, many years, the magnitude of the job was the thing that impressed me, because there's so many different sections of this and so many operations going on at one time, which ultimately build up to the finished article.
Well, the next stage, as far as we were concerned, was the completion of the outlet channel, during which time, of course, the tunnel was being worked. this was the whole key to the job, because the dam proper as such could not be built until the river was diverted. And this diversion took place in May of '62.
We all realised that this was the first milestone in the scheme, because then we knew that we could set about the main task of building the embankment.
A high proportion of the cost of the dam relates to the work required to stop water escaping underneath it, through the foundation and through the valley sides. It was necessary to construct a cut-off to prevent this happening.
In the sides of the valley, the concrete cut-off consists of a 6-foot wide trench filled with concrete and extending to a maximum depth of 90 feet from ground surface to the rock below.
There was a stage in the excavation of the cut-off trench when we didn't know whether it was going to stay put with the shoring that was in to hold up the excavation or not. And each and every time you went down the ladders, you wondered whether you were going to come out again.
It was found from elaborate tests that the cut-off in the middle of the valley need only be taken down 60 feet to a thick bed of clay. Because it would be resting on clay, which would not carry the weight of a concrete cut-off, it was decided to make the cut-off itself of clay, and this was constructed in a large open cutting 60 feet deep.
When you stand at the bottom of a cutting 60 feet deep, you realise just how important safety is. And we were very concerned that the sides of this excavation would not cave in. And the safety was ensured by dewatering in exactly the same way as had been used during the construction of the outlet channel. Now, the object of this large excavation was to connect the top of this boulder clay and to make a watertight membrane stretching from the top of this clay up to ground surface. And then this would be continued, connected to the centre core in the dam by means of a 12-foot thick clay blanket.
Technicians take innumerable series of tests. They treat this material in their laboratories and they decide at what moisture content it is at its optimum densities. Contractors, however, are out on a limb in that they must, for economic reasons, move earth faster than technicians can sample it. It means that the earthworks agent has to take calculated risks within his experience and knowledge to utilize his plant efficiently and to make money for his employers. Sometimes he comes unstuck. This has happened at Derwent on more than one occasion, when I've had to take out 1, 2, or 3,000 cubic yards of materials which failed to pass the test.
The plant is very expensive. Our running costs are high. At our peak period here, when we're using in the region of 5,000 gallons of gas oil per day. A particular tyre costs in excess of £1,000. These machines have enough power to really scrape the tyres, to burn the tyres off within a week. Night work, of course, can be dangerous. Any carelessness whatsoever can indeed have disastrous results. But often I came here in the morning wondering if everything had been all right. Sometimes you jeopardize your day shift by working a plant at night.
The main problem from the design point of view was incorporating the drainage mattresses at intervals within the dam.
Now, the function of drainage mattresses is to let the moisture dissipate. The ground needs to be vibrated underneath the drainage mattress so that you get a solid foundation for this gravel, which will allow free passage of moisture. And apart from our own high standards, these were supervised and inspected and checked by the Southern and South Shields Water Company.
In order to ensure that the pore water pressures are being dissipated correctly, this dam has had incorporated within it a large number of pressure measuring devices. We call these piezometers.
We have something like 200 instruments there, many buried in the foundation, some to great depths, others buried in the embankment itself. There are some 26 miles of nylon tubing connecting these tips.
As you can imagine, the task of reading these gauges during the construction of the dam is quite major.
This network of instruments allowed us to follow the progressive strengthening of the embankment so that we knew whether it was safe to proceed with the raising of the embankment.
In 1965, we found that the pressures were rising very rapidly. After stopping construction for 6 weeks, we were able to ascertain that the pressures did indeed fall, and therefore that our drainage blankets were working correctly.
The shoulders of the embankment are there to hold up the central core. The core and its connection to the cutoff is the part which holds back the water. It is the water retaining part of the embankment.
Something like 2,600,000 cubic yards of material had to be placed in this embankment, which has a maximum height of nearly 120 feet.
The addition of the water doesn't really make any difference to the stability once one has the embankment built to full height. The victory is won.
The concrete blocks protect the upstream face of the earth dam from erosion by the water of the reservoir. In order to produce these blocks, it entailed the manufacture of 180,000, and these were made on the site by the contractor. They were made so that the surface simulated a rock face, and the concrete used was a colored concrete. Not many people will realize that the ground surface under the dam has settled by about 4 feet, and whilst the blocks were being laid, this movement was continually taking place. The engineers set about so that straight lines would be seen by everyone.
Well, I think the biggest problem we had here, and we tackled it very well, was the tunnel stop. We decided that we would do this job at the low flow of water during the year. But much to our surprise, I think we had more water at the time we were putting the stop in than ever we've had since. And there was one night I can remember, we were in the tunnel pouring concrete, dumpers running up the tunnel through the water. And I had to post a chap on the outside to watch the water rise to make sure that we could get out the tunnel on time.
Yeah, the best part of that was pouring the concrete itself. It's the best bit of teamwork that's ever been on the dam, that, I reckon. The controls and the place are blasting the concrete through, and each time it was blasted through, we had to signal out it was clear, like to blast through, and then vibrate it. We took the turns, 2 at a time going in, and 2 coming out, 2 going in. 2 hours each time we took. And the sweat wasn't just coming out, it was running out of you.
The completion of the stop meant that the work was rapidly coming to an end, and virtually the only work then left to do was the laying of the pipes in the tunnel. Compensation water was still being released to the river downstream. The men here did a very good and sound job, working right round the clock, and the laying of the pipes was completed in a matter of weeks. These pipes connect the reservoir with the treatment works some 3 miles downstream of the dam.
Where everything's went underneath, I know the whole valley. Actually fill up's been the main thing, seeing the water come into it.
In the spring of 1966, we stocked the reservoir with 45,000 trout, 10,000 rainbows and 35,000 brown trout. They were adjusted to the new conditions by being put into baths in which there was actually some reservoir water. Then the baths were tilted at the edge of the lake, and the fish were allowed to swim over the lip of the bath and into the reservoir to acclimatize themselves. A process of transition from the nursery into the place where they're going to live and have their being.
There are almost 90,000 trees planted around the reservoir. The main thing is to get them well firmed in so that the wind doesn't blow them around and slacken them. One of the primary things that an inspector has to do is to get it across to the men what the finished product will be, what it'll be like. Once a man understands what's required of him, there are very few men that won't give of their best then.
We've had 1 or 2 tussles with the inspectors, and we've come out all right. We've enjoyed it, really. It's been rough weather. You don't get good weather here, but it's been a pleasure working.
I mean, we've had good chaps and we've had bad chaps, and we've had chaps that want to work and then they don't want to work, but we've had to put up with the whole lot. I mean, they've come and they've gone, and that's been it. And you hear people talking, they say, well, look at the men that's been at the dam. The job can't be any good at all, you see, but it's been a good job.
It has certainly been the most interesting job that I have been on. There have been the technical problems to overcome, which provoked contractual problems. The solving of the contractual problems provokes financial problems. And I was on the tender, and I'm in at the finish. A most interesting experience.
A job of this nature cannot help but be interesting, because it involves so many aspects. It involves the association with our own inspectors. We might have to do small amounts of redesign, alter things, make decisions quite quickly about changes which must be made, because we must always bear in mind that the contractor is here to make money, and any hold-up to plant, machinery or men is money, and our task is simply to be here and to deal as quickly as we can with unforeseen difficulties and changes which must occur on a contract of this size.
The people that have lived here and had their being here for a long time will be sad to say goodbye to the site.
It's not a large town compared with some sites. As we are now, we're shutting a third of the office down, and the dust begins to come out of the cracks. The old files appear. Don't know what to do with them.
I don't regret 10 years on this scheme, mainly because I think we have achieved something which is there for all to see. It will be there long after I'm dead and forgotten about. And after all, the definition of a civil engineer is to direct the great forces in nature for the use and convenience of man.
Now, it would appear to have taken a long time for water undertakers generally to realize that most of their reservoirs are, by and large, a source of impure water. After water leaves the reservoir of this description, it requires a considerable amount of very elaborate treatment. And we, as water undertakers, won't lose any sleep if we thought that somebody had fallen out of a dinghy, for example. We're quite sure that the contribution to pollution made by sailing and fishing is quite negligible. Now, the scope of entertainment and recreation depends in large measure on the way in which the great British public will behave themselves. We sometimes know that litter is a country problem. If the public will behave themselves at Derwent, then the sky is almost the limit in terms of recreational use and pleasure that they can get out of this reservoir.
This job won't be pulled down and replaced by something. This is built into the landscape until it is as near as makes no difference over the years, a fundamental part of the landscape.